Okay, let's slowly start. I probably will only lecture for another 15 minutes, and then I'll give you the paper. So let's see a motion picture of this symmetric mode. How symmetric mode? Again, symmetric mode means the two particles move together, of course. Okay, so without solving any equation, you can probably think in your head that these two particles can oscillate together. So that's the picture. Now, on the right-hand side are the position of the two particles. You can see that actually they coincide with each other. So you see only one curve because x1 is equal to x2. No wonder. And on the right-hand side, you can see what really happened. What really happened. So you have one particle and another particle. If you look carefully and observe carefully, you can see that in this oscillation, the spring in the middle doesn't change length, right? 中间的那个弹簧根本没有改变它的长度。Okay, that's a characteristic and also the mystery. That's why this symmetric mode will move like this. Because if the two particles move together, that means the length of the middle spring does not change their length. Okay, so it's equivalent to K2 equal to 0 because there's no force exerted by the middle of spring on both sides of the particle. So M1 oscillates on its own, M2 oscillates on its own. It's almost a decoupled situation, even though there is a spring in between. However, because of the mode, because of the initial condition, for example here, I put the first particle starting from the point minus 0.5. The second particle starting also on minus 0.5. So that means in the beginning, the middle spring is of natural length. There's no force, okay? So it decoupled in the beginning. And when they oscillate, because they oscillate together, it remains decoupled, okay? So that's why this symmetric mode is so simple. It's obvious, okay? Let me write down here. So the symmetric mode is so simple. X1 and X2 oscillate together. When they oscillate together, the middle spring does not change length. Therefore, they oscillate separately, so the frequency is equal to omega 0. Okay, omega 0. Okay, almost there is no middle spring. So this one only feel the force on the right-hand side, so the frequency must be equal to a single particle and a single spring, which is the square root of k over n. Ditto, the same story for the second particle. So let me now repeat it again. So x1 and x2. But it's not always the story because there are second solution. In the second solution, omega 2 is equal to the square root of 3 times omega 0. Okay, of course you can see that in this case, the middle oscillation, the middle spring must have its effects. Otherwise, the angular frequency will be equal to omega 0. Okay, so let's put this second solution into our equation. Equation is here. Okay, put square root of omega 0 into this omega. Then you get 2 omega 0 squared minus 3 omega 0 squared. So that comes from this omega squared. Okay, and 2 omega 0 squared minus 3 omega 0 squared equals to minus omega 0 squared. Okay, and the second term is minus omega 0 squared, A2 equal to 0. Okay, so cancel out the omega 0 squared, you get A1 plus A2 equal to 0. You can do the second equation, but that's the same story, okay? Then you will see that it is exactly the same equation as the first one, as I mentioned, okay? Because the determinant is equal to 0, so these two equations are essentially the same one, okay? Therefore, it only determines the ratio between A1 and A2 without specifying the constant. So A1 equal to minus A2. Let's call it C2. And again, decompose it into an absolute value times exponential I phi 2, the argument. So now x1 equal to A1 times this, and A1 equal to C2. We can call this A1 or minus A2 as C2. So C2 times exponential I square root 3 omega 0 t. And if you combine the arguments, you can see that it is A2 exponential I square root 3 omega 0 t plus phi 2. Same story for x2, so I don't repeat it again. x1, when you take the real part, it becomes cosine square root 3 omega 0 t plus phi 2. Okay, how about x2? x2 is minus x1, so it's minus a2, the same cosine function. So the conclusion is very simple. So there, even though the formula look very complicated, but as a physics student, you have to concentrate on the essence of this solution. The essence is that the angular, first of all, they all oscillating with time as a cosine function. Angular frequency, square root 3 times omega 0, not the original omega 0. So that means the middle spring has some effect here, okay? So it's square root of 3 omega 0. That's这是一个很重要的结论啊 ，OK， 好，这算了你才知道啊 ，OK， 好。And therefore, this is called, and because x1 is equal to, x2 is equal to minus x1. So that means when one moves in this direction, the other must move opposite. Okay, so it's almost like this. So this is called anti-symmetric mode. This mode is called anti-symmetric mode. But the two are oscillating. Okay, instead of the two oscillating together, they oscillating opposite to each other. Okay, so you see the point? Then I can show you a motion picture again to see the effect of what happened. Now I started the original condition with the first one, 0.5. The second one, I started with minus 0.5. So that means I put them opposite to each other and let them go. And as you expect, the function will be 1 times, the one function will be opposite, will be minus the other. Okay, be opposite the other. And you can also see that the frequency is larger because the period is smaller compared to what we have in the symmetric mode. So that's the effects of the square root of 3. 好，那个根号3你就看得非常非常的清楚，因为它的周期比较短啊，刚刚只跑了大概2圈而已，现在你跑了将近4、5圈啊。OK， 所以呢，它的这个 angular frequency 比较大，那个 square root 3， 就是这样子来的。OK， 那 what really happened is in the cartoon, you can see that they move opposite to each other. So the middle spring has some effects. Okay, so it's really couple oscillation. It's a really a couple oscillation. Any question? So we got a symmetric mode. We got the asymmetric mode. Asymmetric mode. So this is one of the most important message today. I showed you symmetric mode and anti-symmetric mode and how they oscillate with each other and how they oscillate. So in this page, I should translate it in English. So what I have is the two different kinds of mode of oscillation. So that means if you keep the initial condition according to the mode, they will stay in the mode oscillating. Okay, you may ask, how about if I put the initial condition anywhere? For example, in here, in this cartoon, if I put the initial condition, the first one at 0, the second one at minus 0.5, so it's in between symmetric and anti-symmetric, right? So let's see what happens. It's not oscillating. It's a very weird function. It's not an oscillating cosine. But I'm going to tell you, it's the summation of a cosine and a sine. Okay, wait until next week. Okay, so this solution, when the initial condition is not strictly anti-symmetric or symmetric, then the oscillation will not be a cosine function, but it will be the summation of the two modes. That included in Chinese, but I will elaborate that next week. 在这个情况之下，你的开始的起始条件呢，并不是对称，也不是反对称。OK， 那你可以说它是两个的混合啊，对不对？如果你这样想，那就对了。OK， 真的它就是两个的混合。所以呢，我会告诉你，这一个 oscillation 不是 oscillation，OK， 但是它是两个 oscillation 的混合。What does that mean? You can see my transparency, but I will elaborate next week. Okay? Before I let you go, let's rush through the most important concepts today. Metrics. There is a method 0. I told you that this is method 0. So there must be a method 1. Method 1 is the most systematic way to solve this question. And in this more systematic way of method 1, I'm going to use metrics, okay, to simplify the equation. Okay, I'll come back to review this part again next week, but I want to rush through so that you have some impression. And maybe you don't understand it, you can go back home to read after in some pages, okay, so that you are familiar with metrics, column, and all their manipulation, okay? Now, the point is, these are two systems of ODE. So in mathematics, it is easy to write this combination in terms of matrix and column vector. 在数学里面，等到你碰到了一个方程式组的时候，你永远最好的方法就是用 matrix 来表示它。在高中的时候不就这样教吗 ？OK， 好，所以但是如果你不记得的话，没关系，你就去看一下刚刚讲的 Afken 的那些章节。OK， 好 ，Anyway，so let me rush through. So if I collect the left-hand side into a column vector, this kind of structure is called column vector. 行向量啊，所以 with the number on the top, the other number at the bottom, I call it dx1 dt squared, dx2 dt squared. It will be equal to, the right-hand side could be simplified by this multiplication of a matrix with a column. Okay, so if you collect this number here, collect this number here, collect this number here, collect this number here, you form a 2 by 2 matrix. Okay, so the right-hand side can be written as the multiplication of this matrix with x1 and x2. The rule is like this. If you multiply a matrix with the column vector, the first element will be this times a1, s2, 1, 2 times a2. We usually like to draw a line here and then draw a line here so that this times this plus this times this will form the first element of the final column. S2 minus times A1, S2 times plus A2, S2, S22 times A2 will become the second element of the column. That's the rule of the multiplication. It's a rule, but it's a very, very beautiful rule. You better remember it. Okay, and then I have if you want to ask why I use this rule, the reason is very simple. Because with this rule, multiplication will be linear. With this kind of very simplified combination. For example, if you multiply S with C1 A1 plus C2 A2, it could be proven with this kind of rule. Then it could be expanded, just like a distribution law. 跟分配率几乎是完全一模一样的。This is equal to C1 S1 S times A1 plus C2 S times A2. So that's why we design, now we mathematicians design this kind of rule of multiplication between a matrix and a column. And also will be very important, maybe not this week, but will be very important in the future, is how to multiply two matrices together. The rule is almost the same. If you multiply this with this, I use 2 by 2 matrix as an example, but it could be extended to a larger matrix later. So if you do the same thing with this line and this line, do I have line here? Yes. For example, if you want to, these elements, you will do this line and this line together. So S21 times A11 plus S22 times A21 will form the lower left corner of the 2 by 2 matrix. Things like that, please review it at home, either by reading this transparency or by reading the chapter on Afghan. I think it's almost the same, in very near what I write here. Afghan. In the beginning of the second chapter, here, so around page 83 to 88, maybe a little bit beyond, and you will see he reviewed this multiplication rule. So if you are familiar with this multiplication rule, then the system of equation of motion, we can easily simplify into a multiplication of matrix and the column. Okay, so therefore, this equation, we can use a simplified notation to write this complicated equation of motion. If I design X, we call X the column vector as X1, X2. It's a bold letter 所以如果是 bold letter， 它要不呢就是一个 column， 就是一个航向量，要不然呢它就是一个 matrix 你可以 see it's bold it's bold. Okay, so when you see a bold letter, that means it's either a column vector or matrix. Yeah.
三条线是
哪个三条线？
那个等号变三条线是什么意思？
三条线在 define. Sorry, I should have said. 假如等号就是 equal, they are equal. But if you see 3 lines, that means this is defined as this. Okay, because I haven't defined x yet. 我还没有定义什么是 x 粗体的 x 不是小 x. So you have to distinguish. 你要把它分辨，它是粗体的 x 还是一般的 x。一般的 x 就是坐标嘛，对不对？可是现在我这个是粗体的 x， I defined it as the column x1, x2. Is that okay? 所以你下次看到有这个三条线，指的就是我在 define something. For example, here I define A, this 2 by 2 matrix as this. So again, 三条线. Okay, and here I didn't forget the omega 0 is square root of omega k over omega m. Okay, I define this as this. Therefore, this could be simplified as this matrix. It's much simpler to handle than this, right? And therefore, this capital X, this bold X, not capital, bold X, taking second derivative, could be defined as x1 taking second derivative, x2 taking second derivative as the first element and second element of a column. And this is equal to this A times x1, x2. I will define it as A times x. So ladies and gentlemen, all the system of ordinary ODE could be written in so compact notation. Bold x taking second derivative, it is actually this, equal to minus A matrix times x, MH times x column vector. So how cute it is? It's so cute. Oh, it's so cute. This is called matrix notation. But it's the same thing. Actually, when I write this, I'm talking about this. There's no difference between them. But by using a shortened notation, an abbreviated notation, I can write it in a very, very compact form, and it's easier to manipulate. Okay? How easy? I can show you from here. Now, the equation becomes, I reverse the order, minus ax equal to x, taking second derivative. Now, I elevate it into complex number, although in the same notation, but I'm talking about a complex number function. And x, I assume the solution is equal to a times e to the I omega t. Oh, so originally it is x1, x2. x1 equal to a1, sorry, a1 times e of I omega t, x2, a2. x2 equal to a2 times e to the I omega t. Now I can combine them together into one notation. That's the key. I combine them into one notation and assume that the solution I'm going to assume is that a times exponential I omega t. A defined as a1, a2. So with this notation, it means a with upper and lower element, they are both multiplied by the same thing. I probably should write it down. So you will see a1 exponential I omega t, a2 exponential I omega t. But with this notation, isn't it very, very simple? X, bold x, equal to bold a times exponential I omega t. So if I put this notation into the equation, then the left-hand side becomes a times bold a, bold capital A times bold a times exponential I omega t. On the right-hand side, taking second derivative, a is a constant, so it does not have anything to do with differentiation. Exponential I omega t taking second derivative will be omega squared. See my point? So on the right-hand side, I will have omega squared times a times exponential I omega t. And then cancel out the exponential I omega t. I got this beautiful equation. A matrix times a column vector equal to omega squared, a number, times a column vector. Actually, it's an abbreviation of this thing. Ladies and gentlemen, this equation are called eigenvalue problem of the matrix. Omega squared are called eigenvalue, a are called eigenvector. With this beautiful notation, it has a very, very, very simple correspondence in classical physics. Okay, so now with this notation, I can very quickly show you how we arrive at omega. If you are familiar with matrix notation. Look, so I can put tail, any question up to here? So I can take the right-hand side to the left-hand side and combine this with this. It becomes, because there are A, so A can be taken out. So that's why matrix could be manipulated almost like a number. So take this to the left-hand side, take out the A, so matrix A minus omega squared. Maybe I should write an I here so that it's easier to comprehend. So it could be better written as A capital, bold minus omega squared I. I means defined as 1, 1, 0, 0. Okay? So that's a typical way to write this. But sometimes physics are lazy, so they just ignore the I. Okay, the identity 2 by 2 matrix. Or I simply just write it A minus omega squared. Look, so this times A equal to 0. If you have learned matrix, you know that every matrix has an inverse matrix. 反矩阵. You remember, right? There is an inverse matrix. If this guy has an inverse matrix, then A is equal to 0. Because the right hand side is 0. So if this guy has an inverse, then A is equal to that inverse times 0. But 0 times anything is 0. 啊？不懂就问他，对不对 ？Is that right? So inverse times 0 always equal to 0. Okay, 0 means 0, 0. I should say, yeah, maybe your confusion is here. This 0, I mean 0, 0. But sometimes we are lazy, so we call 0, 0 as 0. Okay, so what I'm saying is that A minus omega I minus 1 times 0, 0, of course, is 0, 0. There is no other possibility if this guy has an inverse. So if you want a non-zero A, the only possibility is this guy doesn't have any inverse matrix. For this guy to have no inverse matrix, the condition is the determinant equal to 0. Again, the determinant equal to 0. The determinant of A minus omega. Write it out, it is this. Determinant equal to 0. Exactly the same condition I have. Okay? Yeah, so let me finish it. Let me just stop here. Okay, let me stop here. So this is exactly the same equation I have in the earlier. Okay? Now, just a minute, okay. I'm writing to my daughter, just a minute. And then I'll give you the paper. Okay, so any question about this? So exactly the same solution, and next week I'm going to follow that through by telling you what A will be equal to. But of course, it's the same story. For omega 1 equal to omega 0, A will be equal to 1, 1, dot, dot. Okay, and for omega equal to omega 2, A will be equal to 1 minus 1. Ladies and gentlemen. Okay, exactly the same thing as what we have in method 0. But don't you think this second method is more elegant? I think so. Okay, so